Welcome to the ninth installment of our series, Spectroscopy for Biologists. If you're new here, be sure to catch up on the earlier videos linked in the description. Let's dive straight into today's topic. In this video, we're going to guide you through the process of interpreting an IR spectrum. As we explained earlier, IR spectroscopy is a technique used to identify the types of chemical bonds present in a molecule. It works by shining infrared light on a sample and measuring how the molecules in the sample absorb the light at different frequencies. Interpreting an IR spectrum is like deciphering a molecular fingerprint. Peaks in the spectrum correspond to specific molecular vibrations and functional groups. I'll guide you through the process of analyzing peaks, identifying characteristic bands, and unraveling the molecular puzzle. Let's break down the process of spectral interpretation into clear steps. Step 1. Understand the IR spectrum graph. The horizontal axis, x-axis, shows the wave number in units of cm inverse. Think of wave number as a measure of the energy of vibrations in the molecule. The vertical axis, y-axis, shows the amount of light absorbed. The larger the peak, the more light is absorbed at that wave number. The spectrum represents the intensity of the infrared radiation absorbed or transmitted by the sample at different frequencies. These graphs depict the absorption and transmission spectra. Step 2. Identify the key regions. To do so, divide the spectrum into distinct regions based on the frequency range. The most common regions are the fingerprint region, 1500 to 400 cm inverse, and the functional group region, 4000 to 1500 cm inverse. The fingerprint region contains unique patterns that can help identify specific compounds, while the functional group region provides information about the types of chemical bonds present. Step 3. Identify peaks on the graph. These are the tall spikes that go down from the baseline. Each peak represents a specific vibration happening in the molecule, also known as absorption bands. Each one of these absorption band corresponds to a specific vibrational motion of the molecules in the sample. The position of the band indicates the frequency of the vibration, while the intensity of the band reflects the amount of absorption. Step 4. Find the important peaks. Assign peak positions to the absorption bands based on their wave number or frequency values. Consult reference tables or databases to match the peak positions with known functional groups or molecular vibrations. This step helps in identifying the types of bonds and functional groups present in the sample. For example, alcohol, OH stretch, typically observed around 3200 to 3600 cm inverse. Amine, NH stretch, usually seen in the range of 3300 to 3500 cm inverse. Around 1700 cm inverse represents the carbonyl CO double bond stretching region. Other famous peaks are shown here. Step 5. Analyze the intensities of the absorption bands. The stronger and broader bands indicate higher absorption, while weaker and narrower bands suggest lower absorption. Intensity variations can provide information about the concentration or structural arrangement of the molecules in the sample. Step 6. Consider peak shape. Bands can be sharp, broad, or exhibit additional fine structure. The shape can indicate the presence of different molecular environments or interactions, such as hydrogen bonding or conformational changes. Sharp bands are often associated with isolated functional groups within a molecule. On the other hand, broad absorption bands in an IR spectrum indicate that the molecules are in a complex environment or are experiencing various interactions. Also, this can be an additional characteristic to identify the functional groups. For example, alcohol, OH stretching absorption bands is a broad, strong peak. Unlike, the carbonyl group is found in compounds like ketones, aldehydes, and carboxylic acids, which appear as a sharp peak around 1700 cm inverse. Step 7. Confirm functional groups. Once we get the wave number, intensity and shape of the existing peaks or absorption bands, you can compare the observed bands with reference spectra or databases to confirm the presence of specific functional groups. Step 8. Interpretation. Based on defined functional group, you may be able to figure out the identity of the molecule of interest. But if you don't have enough experience or the molecule is complex, then deconvolution techniques or advanced spectral analysis methods may be required. These techniques help separate and interpret the contributions of individual bands and aid in the identification of complex molecular structures. To truly grasp the power of IR spectroscopy, let's explore of captivating case studies. One famous compound that has been extensively studied using IR spectroscopy is aspirin, acetylsalicylic acid. Aspirin is a widely used medication with analgesic, pain-relieving, anti-inflammatory, and antipyretic, fever-reducing properties. Spectral interpretation. The obtained IR spectrum is analyzed to identify the characteristic absorption bands and infer the molecular structure of aspirin. Firstly, the fingerprint region provides unique patterns that are characteristic of a specific compound, which is aspirin in this case. Secondly, functional groups. Carboxylic acid. Aspirin contains a carboxylic acid group, COOH. This functional group typically exhibits a broad and strong absorption band in the range of 2,500 to 3,300 cm inverse, due to the stretching vibrations of the OH bond. Ester functional group. Aspirin also contains an ester group, COO. The CO double bond stretching vibration of the ester group is observed as a sharp peak around 1,700 cm inverse. Aromatic ring. Aspirin possesses an aromatic ring in its structure. The presence of aromatic rings can be indicated by absorption bands in the fingerprint region, 1,500 to 400 cm inverse. That was everything for this video. Thank you for watching.